Okay, good morning, afternoon, or evening, everybody. Welcome to the Gregory G. Leptoukh 4th Online Giovanni Workshop. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Time, so we are going to go ahead and get started here. We'll continue the Giovanni Workshop today with our final webinar. Our speaker for today is Dr. Guido Cervone. He is the Associate Professor of Geography, Meteorology, and Atmospheric Science, as well as the Associate Director of the Institute for CyberScience at the Pennsylvania State University. He will discuss how he uses Giovanni and R as part of his undergraduate remote sensing class. Before we begin, let's quickly go over just a few logistics for today's webinar. To ensure the best audio experience, participants have been placed in silent mode, but if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A pod, and you'll find that located on the right-hand side of your screen. This works like a chat. Today's webinar is being recorded. The recording will be posted to our online Adobe Connect webinar catalog, as well as to our NASA Earthdata YouTube channel within a few days of completion. I've actually created a separate playlist for the Giovanni Workshop this year. Once this has been completed, what I'll do is I'll send an email to all webinar or workshop registrants with the recording links. As far as timing is concerned, today's webinar will be 1 hour long, with 45 minutes allocated to the presentation and live demonstration, and an additional 15 minutes for the question and answer period. Once our speaker for today has finished with his presentation, we will transition to a final optional set of polling questions. We'll give the questions 3 to 4 minutes or so, and then from there we'll move directly into the Q&A period. And depending upon the volume of questions that we receive today, we will extend the Q&A period an additional 15 minutes from end time for those of you who may wish to stay on the line, with a hard cutoff, however, of 3:15 p.m. Eastern Time. All right, at this point, what I'd like to do is turn it over to Dr. James Acker, who is the Giovanni Workshop organizer, for a few opening remarks. Dr. Acker?
Thank you, Jennifer. And first of all, I want to thank Guido for participating. We communicated with Penn State over the last year or so, and Guido is a avid and active user of Giovanni, and I think he was also inspired to do what he does by Greg Leptoukh, and he may expand on that a little in his introduction as well. I also want to thank Jennifer for setting up the Giovanni playlist, the workshop playlist, which we will link to. I know that we have a worldwide audience because I've received inquiries about it, and I know that we had well over 100 registrants for the webinar series of this workshop. So I think that'll be useful. One of our partners, the ESIP Federation, is going to link to that playlist when it's available. So we should have a lot of views subsequent to this live presentation. So again, I want to thank Guido and find out more about what he has to say. I've seen some of the things he does, and they're quite interesting. Okay, thank you, Jennifer, and thank you, Guido.
Okay, at this point, we'll turn it over to Dr. Cervone. He will share his screen and begin his presentation. Thank you, everybody.
Hello, everyone. My name is Guido Cervone. It is truly an honor to give this cyber seminar. Thank you, Jim, for inviting me. Thank you, Jennifer, for really helping me learning how to run this seminar over the last 2 weeks. So, as Jim said, I'm an avid user of Giovanni. I'm a professor at Penn State. I teach courses both at the graduate and undergraduate level. And I normally use Giovanni to teach the students how to do some simple analysis online before downloading the data, then download the data, and then do some further analysis on their own computers using a variety of tools. Today we'll be looking at R, which is one of the primary tools I use, and also QGIS. Both tools are free of open source. They're free of charge. You can download them on the internet. And I will show a little bit, some quick demonstrations of what we can do, but I hope that this will inspire you to see all the great opportunities that you have to analyze data using those simple tools. So I'm, as I mentioned, I'm a professor at Penn State. I've been teaching remote sensing for about 12 years now. And both at the graduate and undergraduate level, I mentioned before. And definitely Giovanni and Greg had quite an impact on my own education and also on my own really philosophy, like teaching philosophy. And I'll tell you a little bit more. So a little bit of history. My background is in computer science. I did a bachelor and master in computer science. And while I was doing my PhD at George Mason University, I believe I was in my probably third year of my PhD. Up until that time, I developed a methodology for spatiotemporal data mining and machine learning. And I was just very proud of my methodology, but it was very theoretical. I was looking for some real data to use, that I could use. And just by chance, I walked into a seminar, and Greg was giving this seminar. And that was the very first time in my life that I saw remote sensing data. I believe it must have been 2000 or 2001. MODIS was very new, and Greg gave a presentation showing some MODIS data. And in particular, if I remember correctly, it was showing how average data would just not match I think over the Pacific. And I became, very intrigued. First of all, I asked, very silly questions was, well, is this data classified? Because I remember at that time, I thought that all machine learning data, or remote sensing data must be property of the military. And really, this is how I got into remote sensing. So Greg was definitely had a very strong influence on me. I believe Greg had an appointment at George Mason University, a courtesy appointment, because throughout my studies I met with him many times. And I believe that this is around the time when Giovanni really started, or at least, the initial idea of Giovanni started, to download data and also to provide an analysis tool so the students can very easily access the data. The remote sensing course I teach at Penn State, the undergraduate remote sensing course I teach, is called Geography 362, Observing the Earth and its Environment. It is at the undergraduate level, even though occasionally graduate students ask to take the course. The students come primarily from geography, meteorology, geosciences. Those are very bright students, are among the best students. It is a third year course, so we can assume the students have already taken some math course, some geography course, but no remote sensing, absolutely zero. And it's a very hands-on class. There is 3 hours of lectures, usually twice a week, plus 2 hours of laboratory. The main tools that we use are QGIS in order to make the maps and R in order to perform the maps. And the data, it's paramount. Many of the students, they have difficulties, finding data. They have to define a project and look for data. And it's very important that they learn where they can get the data from. So the primary tools, or I would say portals that we use, are the Earth Explorer, the NASA Worldview, the HTDS, which is the Rapid Disaster Response website from USGS, NASA Giovanni. I said I'm a very big supporter of Giovanni. The NASA NEO, that's another very easy to use website. The data set from the Lamont repository, primarily for model data. We also use data from NCAR very extensively. This is weather model, either the global forecasting system model or the WRF model. And then NOAA high split, which is a Lagrangian transport and dispersion model from the Air Resource Laboratory. Use those tools throughout the class. There are several opportunities for the students to download their own data and to do their own analysis. What I will show you today is a combination of a little bit of Worldview, the NASA Giovanni, and NOAA high split. In the later part of this presentation, I will show you those tools online. Some of them take quite some time, so I've preloaded all the data, but I will show you how to run them. We will just not wait for the data to be generated because that would take too long. A typical assignment is that I give them an article about a recent event, something that can be observed from space. Normally is a natural hazard or a disaster. Things that we study are, for example, volcanic eruptions or floods or forest fire. We start, so I normally go to class and I start with a presentation where I show them, well, this event happened X days ago. And then I try to give any news reports that use remote sensing data to cover this particular event. And then, we discuss the data in general, what is available, what is not available, why certain products were used. And then we go ahead, we try to download the data, try to plot the data, and then whenever possible, compare with some numerical model data. What I prepared for today is atmospheric dimming caused by forest fires in Canada. So the event, the main event is on May 30 to May 31st, 2019. This is what you can see here on the screen is screenshots from the Science Discover, which is a very interesting blog about science issues. What you see at the bottom left is the smoke, the model smoke from NOAA. Top right is GO-16, where you can see the plume. And in the center is a modest image. I circled it with a red ellipse to show the plume. It's not very visible. Don't worry about it. We're going to see it in greater detail in a little bit. So this is how the class starts. I give this article, give a little presentation, prepare the data, and then we have a discussion on what we can and what we cannot do with the data. The first step, as I said, explain the data. In this particular case, we'll go over aerosol optical depth, what it is, how it is derived, what are the uncertainties, and how we can get the data. In this particular case, I will go over MODIS, the Terra Aqua, and also over OMI, Onora. I will talk about the different resolutions, the spatial radiometric spectral and the temporal resolutions. Keep in mind that those are topics that the students are very unfamiliar with. When we talk about spatial resolution, most of them are familiar with Google Earth. So, they think that all satellite data comes with a sub-meter pixel resolution. And they're only familiar with the visible part of the spectrum. So we need to explain that scientific remote sensing data often has a lower spatial resolution, but a larger spectral resolution. And in particular, I spent quite a bit of time to talk about what are the derived products, things like aerosol optical depth, versus the raw reflectance or radiance that we observe with a satellite, which also can be obtained. The future steps usually involve explore the area using Worldview, find Worldview to be a very good tool to have just an idea of the area. It's very easy to use. It uses an interface that the students are very familiar with. And then we go ahead, we download the data using Giovanni. We load the data in R. Once we download it from Giovanni, we start generating some plots. After that, running NOAA high split, the atmospheric model. This can be run from a website. I have pre-computed it and preloaded on my machine right now because it takes about 30 minutes or so to run the model. And once we have all those data, we load Quantum GIS, QGIS, and R, and we try to compare the satellite data with observations. satellite observation with numerical observations. And this includes both qualitative, just looking at maps, and also quantitative, so just to make an assessment like area averages, minimum, maximum, histograms, so on. And then the students have to turn in a report where they comment and explain. I usually try to ask them to critique the original news article, whether or not the initial coverage was accurate in their opinion. Maybe sometimes those are rapid results, so there are no new data, so there are some speculations in the articles about what will happen in the future. And I ask students to comment whether or not they're able to prove or disprove the initial theory. So I will go on with the demonstration and the three tools, 4 data sets we're going to use is from NASA Worldview, then NASA Giovanni. Then I also download a population data set from the NASA CDAC. This is Socioeconomic Data Application Center. It's maintained by Columbia University. And then as I said earlier, the NOAA high split, this is the transport and dispersion, Lagrangian transport and dispersion model that we use in order to simulate the flow. Okay, so I will first go to Adobe Connect. I will just, I assume that there are no problems, that everybody can hear.
We can hear, but what you're sharing on the screen currently is the Adobe Connect interface.
Yes, yeah, that's correct. I just went back to look at the chat. I just wanted to make sure I'd not been talking for 15 minutes to nobody. Okay, so the next step, as I mentioned earlier, would be the Worldview. And I'm sorry. This is the link that I provided in the presentation, and I'm sure this presentation will be available to you. By the way, I will just teach something that Jennifer taught me just a few days ago. If you click here on the link, you can shorten the link, come up with something that is very nice and compact to share with others. Even though the link, this option is there, I don't know why I never noticed it. So I've always been sharing, the very long version of this link. Okay, so the reason why I like to start with Worldview is because students are very familiar with this interface. It looks very similar to Google Maps. And I mean, of course, we have the slider for the time. This is May 30, 2019. So this is, I assume you can see my my mouse. You can see here, this is the primary emission. So this is the big forest fire. And what I showed you earlier in an ellipsis was actually this area right here. So this is what it was in the news article that was identified as a dimming of the atmosphere. It would be this part right here as observed by MODIS. So what I preloaded here in Worldview is the aerosol optical depth at absorbing at 388 microns. And I just added, and you can see how this corresponds with our original flow. I will also have the students go a little bit back and forth. Let's see here how it works to try to see the temporal evolution. And this is primarily so that they can understand what kind of data we should go ahead and download. What I've also preloaded here, let's see if this one works, is the population density map. This is the NASA CDAC product. Here I'm showing the version for 2015. And that is important because I generally ask the students, can you estimate how many people roughly have been affected by this particular event? In the case of an atmospheric emission, it's a little bit more complicated, but when we study floods, for example, it gives us a very good assessment of how many people were affected, and which is also proportional to the severity of the hazard. So with this particular tool, the primary goal for the students is really to try to understand what is the time frame to which they have to download data. Once they do that, and let's see if I apologize for this. I had preloaded Giovanni, but I must have closed the tab by mistake. Apologize, my internet is a little bit slow. Internet is extremely slow.
So we do see you are hovering over the NASA Giovanni.
Yeah, I'm trying to load the website and it's not loading. Apologize for this. Let me try again. That's very strange. Should be just okay. I'm not sure why this is not working. Okay. And I truly apologize for this. I preloaded it, but while I was clearing my desktop for this,
So one suggestion might be just try typing the URL directly, Dr. Acker said.
Yeah.
Because Giovanni is up currently.
Yep. No, I'm sure it is. Yeah,
Thank you for your patience, everybody.
Yes, I'm sorry. I cannot see through my... Okay, what I'm going to do, I'm going to try to shut down my browser and load it again. I think it's the most sensible thing to do. Yeah.
Thanks for your patience, everyone.
Yeah, I am sorry. I don't know what happened. I should be logged in right now. Okay, so after that initial exploration with Worldview, the students will start doing some initial analysis in Giovanni. The first thing would be a time average map. And actually they would try a few of those. You know, I asked them to do a time average map. I'll ask them to do an animation. I asked them to show me the accumulated dosage, and then to start doing some comparison, some correlation, some scattered area, and so on. So really try to explore the data as much as possible using the online tool. One thing that is very important for me is the time series. So trying to understand whether it's possible to see the evolution for a particular area. Now, I want them to do the initial analysis in Giovanni, and this is primarily so that they know what to expect. And then I want them to download the data and do the very same analysis in R, so that they can learn how to actually do it. So I use Giovanni just to explain to them, so that they understand what they are supposed to get. And I found this to be absolutely of tremendous importance for students, because sometimes, again, this is a first remote sensing course. They really walk in the dark. They really don't know even what to expect. And I think that the biggest advantage of using Giovanni to teach remote sensing is that the students easily understand what to expect, and then they can go ahead and do it on their own. So I'm going to show just, as I said, I have preloaded several of those things. So I'm just going to show you one example, and then and one example right here, and then we can move on. So we're looking at between basically the 29th of May and the 3rd of June. This is the time where it's important to study this particular event. For the area, I'm going to select roughly this area right here, and I'm going to select the aerosol from OMI at 388 absorption. And we plot the data. Usually it just takes a very few seconds to do this little exercise. Okay, so while the data are being generated for us, okay, here it is. So here we have a time average map for those days that are identified, and the aerosol optical depth. Here we can do several things. One is to download the data as a GeoTIFF, which of course it's important because GeoTIFF can automatically be loaded both in QGIS and in R. But I want the students to go a little bit step further. After they're done with this Giovanni analysis, I tell them to go to Lineage and to actually download the original data file that you can find here under Output. So those are the NetCDF files that were actually used in order to generate this time average map. And the reason why I want them to work with NetCDF data, it is because they need to understand, first of all, one of the most used scientific formats, but also the concept of a container data set. So you're all very familiar with GeoTIFF, but once we get into the NetCDF, it gets a little bit more complicated for them because NetCDF, they vary very greatly depending who generated them. There is not really a standard way to encode data. Sometimes longitude and latitude are stored as long and lat. Sometimes as we spelled out longitude, latitude. Sometimes as X and Y, and so on. So I asked the students to go ahead and to download each individual file and start their analysis in R. So I'm going to close this. This is a very simple code. I have to admit, I actually wrote this code earlier today, this morning. Usually I give the students a little bit of a more complicated code. I really simplified for this particular webinar. And by the way, this is available. I'm very happy to make it available to everyone. If you're not familiar with R, this is an open source language and environment. What I'm using here is called RStudio, which is a graphic interface for the R package. By default, it is divided into 4 different quarters. The screen is divided into 4 different quarters. The top left quarters is the actual script. The bottom left is a terminal. So it's interactive terminal, so we can give commands, and those will be executed in real time. What we have on the right, we have different tabs, are the environment variables, the history of commands that we've given, connections, we can skip it for now. Here at the bottom left, again, we have different tabs. Plots will display any graphics plots, and we'll see a few of those. Files will show the files in the current directory. I created one called NASA Giovanni for today, and then we can skip the other ones for the time being. So what you see here, those scrubbed files, those are the individual NetCDF files that I have downloaded from Giovanni, and this is the GeoTIFF also downloaded from Giovanni. Let's go over the scripts. It will just take a few minutes. At top, under library, we have to load basically the packages, the libraries that we use to for our code. In this particular case, I'm using netcdf4, which is a library to read netcdf file. Raster, it's a library in order to generate, as the name implies, raster images. Maps, so we can add a map, coastline in this particular case to our maps. And our GDAL and our GEOS are libraries that give us commands in order to manipulate spatial data. So the first command, we define a coordinate system. In this case, is a very simple, unprojected longitude-latitude system. This is the file name for one of the files I downloaded from Giovanni. In this particular case, this is the 31st, and then the variable names. This is the variable inside the netcdf file that was generated, and I will show you in a few seconds how to actually retrieve this one. This is a function that I created to read Giovanni data. All I need to pass is a file name and a variable name, and what the code will do is, again, define a basic projection, open the file name, extract. I think there is a little bit of feedback on the microphone.
So if somebody needs to mute themselves, please.
Yeah.
Thank you.
Okay. Yeah, I think it's working right now. So we open the file, we extract the data for the variable name. We have to do a little transformation to transform it in R. It's basically just a transpose and flipping. Then we download longitude and latitude, and then we generate a raster, and then we return this raster. So everything is already loaded in my memory. Right now, I'm just going to execute those 3 commands. And what this code will do is to read the file name that I gave and extract the variables. It takes just a few seconds. Normally it is much faster. I noticed that when there is Adobe Connect in the background, it's just a tiny bit slower. So this is the data. Is for the entire world. But again, I loaded just one image. This was for the 31st of May. This particular command, it's a regular expression, and I'm telling R to list all the files that started with the word scrubbed, then there is everything, and then they end in NC. So if I execute this command, those would be our files from the 29th of May until the 2nd of June. This is a little trick. If you see in the file names, we have, the year, month, date. So I just wrote a little regular expression in order to track that. And those are our dates, again, from the 29th until the 2nd. And then I create a linked list, and then I read them. So what this command is doing right now while I talk is loading each one of the file, and then it is converting it into a raster. Brick is a command in R, which is a multi-dimensional raster. So this is basically it's a raster with multiple dimensions. In this case, we have 5 dimensions. Each dimension is a different time. I'm going to execute it. The next command on line 45, this is showing, right here, is showing the first layer in this brick. So this will be for the 29. So it will look a little bit different than what was shown before. Similar, but a little different. And again, I apologize. It takes a few seconds to load when there is Adobe Connect in the background. Otherwise, it would be almost instantaneous. So basically, we loaded the file, and this is for the whole world. The next step that I'm going to do is to define and extend. going to be somewhere over here for now. And then I'm going to plot just the data in this particular smaller subset. The next thing that I normally ask the students to do is to generate histograms. Histograms are very fast to compute, and they give us such a good idea of what the data are. So this particular command divides the screen into 5 different layers, and then it plots the histogram for each of the layers that we have extracted. This is specifically the AUD values, aerosol optical depth values for the extent that we have defined. And then I asked the student to generate a time series for a point. Now it's a little bit I'm going to generate just one point, somewhere around here. It seems to be a good point to pick up. Then, because there are so many missing data, generally I ask the students to create a buffer around that point. What you see on the screen with the circle, that is the buffer. Then we extract the values for this particular point, and then we plot it. So in this, there are still, some missing values, but of course, each point that we determine, that we pick up is a little different. And the students can start seeing what is the evolution over time for different regions and different points. So this is a typical exercise. The next step would be to load our QGIS. So there are different things that I ask the students to do. One is that in R to generate some either GeoTIFF or shape files that can be imported into QGIS. And in this particular case, what we have, and hope it's clear, those are the 5 different layers, which is the aerosol optical depth again. I don't know what just happened. Yeah, the 5 different layers from aerosol optical depth that we defined from Giovanni. And QGIS, it's again, it's a little bit more of a familiar tool for the students so that they're able, to better zoom and inspect the values. For example, right here, we can find that the aerosol optical depth in this particular region was, sorry, I was on the wrong layer, 0.496. Okay, so the next step, as I mentioned before, is the population. So this is the NASA CIDA, and I asked them to load the population data so to have an idea of how many people could have been impacted by a particular hazard. Now, at this point, we know the population, we know those clouds, those aerosol depth as seen from the satellite. The next step is, well, can we compare with a numerical model? And for this particular exercise, we're going to use high split. Now, let's see if I can show this to you. I'm going to load it again. Okay, perfect. So I'm going to load this NOAA high split. It's a very, very neat portal because it allows to run the simulation on a website. So, so I pre-computed it. I will just show you how to run it. This is the high split model. Those are the little description of the model, of how it works. and you can run high-split either from a website right here, or you can download and run it on your machine. Of course, the options on the website are a little bit limited, but I can just show you how to set it up and run it. We're not going to wait for the whole simulation because, as I said, it will take quite a bit. So we're going to run a dispersion model, and we're going to run an archive dispersion, little warming. We have different options here. It can be a prescribed burn for forest fires, it can be volcanic ash, or we can just have an unknown materials. I'm going to go with an unknown materials. There are several different atmospheric models that can be used, from high resolution, like NAM, this is a North American model. This is for only the contiguous United States, all the way to GFS, which is the global forecasting system. Keep in mind that this is quite a high resolution. It's only available for the last few months. This is on a rolling basis. And then we have GDAS that is present, the 1 degree version from 2019, or we can use the previous version, which is available from 2006. In this particular case, it doesn't matter. We can use the 2019. The source location, just a second, it has to update our map. But the source location is roughly about here. And again, normally it works extremely well. I think it's because Adobe Connect is running in the background. My machine is much slower than usual. But it's a very simple to use. Yeah, I think it's somewhat has crashed on me. You select the source, and then if this works, we can go into the second week of June, and well, we just select the date, the release. It's 24 hours released, and we want our simulation to run for 24 hours with an output every 1 hour. As far as output, we can have some GIS contours. The two options are either Google Earth KMZ or GIS shapefiles. What I've pre-computed for you are the GIS shapefiles. Those are shapefiles in the Esri format that can be loaded both in R and in QGIS. And those are just, for different outputs, whether in addition to the layers you also want to have, some GIF or PDF and so on. You just request the dispersion run and let it run. This will take about 30 minutes or so in order to generate these 24 hours simulations over such a large domain. As I mentioned to you, I pre-computed it, and those are those GIS layers from 1 to 24, and I'm going to turn them on one by one for you, and you will see the simulations. So we are right here. This is how I need to give it a few seconds. Yeah, my QGIS is catching up with me right now. As I said, QGIS has to catch up with me. But this is the simulation, and it's so it's a real numerical simulation, which is based on the model atmosphere at exactly the dates of the release. And right now, each layer is just a flat color, but if you want, you can actually color code the concentration. And then we can look at our Giovanni average map. I will move this as a first layer so that it will be on top of all the other ones. And at that point, we can start looking at, whether or not there is an agreement between this time average map and the individual simulations, or the individual days. This simulation was done, for the 30th, so it should be most in agreement with this layer right here. The next step is for the student to quantify them, so to come up with time, to generate time series, and then write some final report as whether or not what they have analyzed and seen is consistent with what was presented in the original act. So I think, that I
transition to an optional final set of polling questions, and then from there we'll move directly into the question and answer period. So let's give these questions just a couple of minutes or so, and then from there we'll address any questions you may have. All right, thanks everybody. All right, everybody, we're going to give these questions another 30 seconds or so, and then we will transition to the question and answer period. Okay, everybody, at this point we will transition to our question and answer period, and while I am waiting for any questions, I want to draw your attention to today's presentation. You'll find that in the lower right-hand corner. If you highlight the file, you will be prompted with an option to download Dr. Cervone's presentation from today. All right, are there any questions? Let's take a look here. Okay, so the first question is, and a comment combined. Excellent teaching idea to download the NetCDF output and put it into R. Can this also be done with oh, okay, excuse me. It's more of a comment. This can also be done with Panoply. Are there any questions from anybody? Okay.
I see one from Jim about running Giovanni in the cloud.
Okay, can you, let's see, I'd like, Guido, I didn't see that because you had responded. My apologies. Let's see, I'd like Guido to comment on the potential of having a cloud Giovanni for both machine learning research and for teaching.
Yeah, so I actually asked privately Jim what he meant by a cloud Giovanni. In the past, yeah.
He said Giovanni capabilities will be deployed in the cloud.
Well, so let me start by answering that. Any effort in making Giovanni more available and easier to use, of course, I think is extremely commendable. One of the ideas that, I discussed with some of my students, and I don't remember if we talked with Jim about this or not, is that the kind of analysis that are allowed right now on the web interface, they're extremely good, like time series analysis, averaging, and so on. And as I said, those are extremely good because the students can have an idea what they're looking for and then reproduce it. Now, one idea would be to add some more advanced tools in Giovanni that are not as easily replicated. And machine learning tools are definitely some of those. And what I'm thinking about it is, for example, cluster analysis or just classification. Let's say that we create multiple layers, for one specific event. And this could be some aerosol optical depth, maybe some precipitation, maybe something that, we can see on the ground. Well, can we run some cluster analysis for those pixels? And then, can we find, for example, similarities in the data set? Something that I believe students would find it extremely helpful is if there is an extreme event that we have noticed in a specific area as well, can Giovanni help us identify it automatically? What are similar events that occurred in the past 10 years? This would be something that, it's not easy to do right now, whether we're using Giovanni or, even more doing it by downloading all the data. So that would be something that I think would be highly desirable, and a cloud solution might be able to have the computational power to allow for this type of analysis.
Okay, thank you, Guido. So we do have a couple of other questions as well. The first one is there any book on spatial plots with NetCDF HDF using R?
As far as I know, there are no books, but there are quite a few online tutorials. The one that I point my students to is called Spatial R. So it's enough to Google for Spatial R, and there are several tutorials on using raster spatial points data frame, or the SP package. And one of the examples talks about how to load and save R files. It is actually not very difficult as long as the data, they are represented on a matrix. What happens is, for example, the output from WRF, they're a little bit harder because they are on a non-standard grid. And what is necessary to do in that case, or at least what I've done in the past, because I found it to be simplest, is to download the data, so the matrices, download the representation, longitude and latitude for each pixel, represent them as spatial point data frames, and then to run an additional interpolation over the data. That I know that it has sub-artifacts, but it is a lot easier than trying to absolutely match the WRF or any other model's non-standard grid output.
Okay, thank you. And then I did want to add for this user that we've held at least 2 webinars that focus specifically on manipulating NetCDF output and HDF using R and Python. So I can follow up offline. And in fact, there are several scripts and recipes that have been made available as well. So I can follow up with this user offline. And then the next question is, do you have any suggestions on how to improve Giovanni? For example, what about adding level 2 data?
Yeah, I would love if it was possible to download, the satellite radiances, because one of, as I said in the presentation earlier, I use this as an opportunity to explain the difference between the products, like aerosol optical depth, and the actual gradiences or reflectances that are measured by the satellite. So to provide those would allow us to do additional exercise for the students and also generate the products, apply the algorithms in order to generate the products. Of course, some products are very hard, others are much easier. But that would be one very nice addition. Another idea to, for adding level 2 data is to do the type of cluster analysis or maybe similarity analysis that I was mentioning earlier.
Okay, thank you. Another question is, do you find R to be a better language for analysis than Python?
Oh, thank you for this question. This is an excellent question. And I must admit, I struggle with this every year. So I actually can, as I mentioned, I'm a computer scientist by background. I can actually learn, I can program in R and Python. The reason why I'm using R is that most of the students are from a meteorology, geography, or geoscience background. Those are students who have, for the most part, have never been exposed to programming. Sometimes they had a little bit of MATLAB programming, but for the most part, they don't have any R or Python or other languages knowledge. It turns out that R is a lot easier than Python because in order to properly teach Python, even just the idea of objects and object-oriented programming, it's something that takes quite a few weeks, for the students to really master. Whereas in R, it's easier for me to get into the class, give them the script, just sequential script that they can run line by line by line. They don't necessarily understand each line, but they can understand what is the relation between, what they're typing and the output. So I actually think, Python is a more refined language, definitely. It is probably more appropriate for numerical solutions. When it's a matter of giving some tools so that the students can do some analysis, spatial analysis, I found that R is just simpler for the students. So I don't think that, one is better than the other. I actually found them rather equivalent for many tasks. Python, as I said, is probably a little bit more advanced for the numerical analysis. R is more advanced for the statistical analysis. But R is definitely easier to learn to write simple scripts. Now, as things get larger, then probably Python will be more maintainable. But that's my take. So the reason why I use R is just because it's easier for my students to pick it up, not because I think it's necessarily better.
Okay, thank you. We appreciate that response. Are there any additional questions? Just taking a scan through here. Yes, okay. So the next question is, can we get the Giovanni product in high resolution level 3 data in the future, like MODIS land surface temperature in 1 kilometer resolution? That might be a question for Jim.
Correct. I was going to refer to Jim.
Okay, Dr. Acker, did you want to provide additional details?
Yeah, if you could hear me, it's always been a matter of what is available to be put into the Giovanni system and our system resources, partly because a 1 kilometer resolution data set is a big volume. And we, as I even alluded to in my own presentation last week, Giovanni's been remarkable for running on the same basic hardware for a long time. And that's not a big supercomputer. It's just your basic standard, data computing system. So there would be a lot of considerations to go to a higher resolution. I sometimes work with ocean color data. That's at 4 kilometer resolution, and I can see the difference in the processing speed compared to something that's like a 1 degree or even a 1/4 degree like you commonly see with atmospheric data. So there's a lot of considerations. It's not unheard of. And again, the Cloud Giovanni potential is for faster speeds and potentially for data sets like that to be in the cloud where you could get them. So there's a lot of stuff out there that we're thinking about. Since I'm talking, it's some of the things that we might even discuss with Penn State as they approached us for possible collaboration ideas. And so I'm going to be in touch with Guido and a few other faculty members about moving forward on that this fall. So that's where we are right now.
Okay, great. Thank you, Jim. All right, are there any additional questions? Anybody? Okay, if not, what we'll do is we will log off from the audio component of today's webinar, and we'll leave the virtual meeting space open an additional 10 minutes for those of you who may think of something you had not mentioned earlier. You'll still have an opportunity to add that into the Q&A pod. All right, any additional questions? All right. At this point, we will log off from the audio component. I'd like to thank all of you, especially our speaker for his presentation today, as well as Dr. Acker. All right, thanks everybody. Jim, did you have any final remarks?
No, I'm good. Thanks, everybody. And remember to look for the playlist.
All right, perfect.
Goodbye.
All right, goodbye, everybody.
Goodbye.